Okay. So who knows? This ever might be a short class, or I might just keep rambling about numerical integration out of sheer boredom, or who knows? If you got homework questions, we certainly have plenty of time for those. Don't you all have something going on in whatever other classes? I remember Walker, you telling me something about that, like in 605 midterm or something. Yeah, and then and real analysis. Yeah, a do-over. So, yeah, that's nice to see that Dr. Ding's classes continue to play out exactly the same way every single time. Why break tradition? Well, okay. Well, all right. So half the class is going to be occupied with all that. Okay. Now, or I guess more than half. But in what time you've been able to spend on homework, is there any actually, or maybe you're kind of between assignments right now? I'm not really sure. I just graded a few. Are there any homework questions out there, or?
I was really struggling on that last one. Just figured it out. So I'm in the in-between of just finished 5 and we'll be starting 6. So I don't have questions yet.
Okay. Which one was that that you just figured out?
The A, C equals B, the matrix, and all the coefficients you have to solve for.
Okay.
7.6.5, I think.
Oh, that one. Yeah. Yeah, that's what I used to do when I would cover this section in whatever class, like 460 or 560 or equivalents thereof, is I would actually derive that whole system of equations. In other words, doing exactly what you just did in this problem, and I never liked doing that because it always would have been like a year at least since the last time I did it, and I could never remember how I figured it out, and the thing is, I gave you guys a hint to start with the right-hand side and work your way back. And I wanted to try to do it in a way that was not so pulled out of thin air as that, which is even harder to do. And I guess when I wrote the book, it's like, you know what? No, I'm doing what every other evil mathematician author has done ever. Leave it as an exercise. That used to be a lot. Okay, calculus. And when you took Cal 2, doing integrals, one of the things you learned about was like volumes of various shapes using disk method, washer method, all that stuff. And that's something that used to be just an exercise in a calculus book, and then they decided to bring it out of that and just make it its own section and like actually teach it. Here I am going the other way. But hey, you guys were able to do it. So that's good. Because especially for mathematicians, that which doesn't kill you makes you stronger. So.
Yeah, I'm in the same area, but in that last one, it'll take a minute.
Yep.
So it may be tomorrow. It just depends on the motivation after running today.
Okay.
But it's also between assignments.
Okay. Alrighty. And same with everybody else.
Yeah, I'm similar, I guess. Haven't figured out the last one, but I'm in homework 5.
Okay, good.
Yeah.
We'll see how that goes, but you have empirical evidence that it's doable. So, okay. All right. So, so whereas splines is not really one of my favorite topics. I mean, yes, I do appreciate its importance, but still, I mean, and about there are going to be preferences, and if if any of you end up going with an academic career, you'll find that there are certain days like, okay, what am I covering in whatever class today? I'm like, oh, this, yay. And I guess you might be experiencing that already with college algebra. Or maybe that's the norm in that class. So I'm my other class I'm teaching 326, which is our first linear algebra course. And I thought, oh, it's my first time doing it. It's like, oh, I love linear algebra. You will see, you all four of you will see next semester just how much I love linear algebra. I do not like this introductory linear algebra class. It just, no. So I guess go figure. Like today, it's like, oh, I'm gonna talk about properties of determinants. Okay, sure. Yeah, and the nice thing is, as a professor, in some cases, you could be like, you know what? No, I'm not going to cover it because I don't like it. All right, you shouldn't do that in the middle of the calculus sequence because people have, expectations. But still, now and then, you can do that. But I almost didn't bother with splines with you guys. But was like, well, okay, it is important, so fine, I'll do it. Okay, but now we're getting something that at least appeals to me more, and hopefully it'll appeal to you as well. Okay, now that we've seen numerical differentiation, now we'll go the other way. Come on. All right. So integration. All right. So you're given some function f of x, and you're given an interval AB, and all you're looking to do is an approximation of a definite integral of f of x from a to b. And some books will use this kind of strange notation to refer to the exact value of the integral, like I of f or something like that. All right. So now, of course, this is a problem that is quite familiar to all of you. And if you look at how do you go about solving this problem currently, you just find an antiderivative. Big F, little f, and then you just plug in the endpoints and subtract. So I want to give some examples of when that is not feasible. Because in your Calculus 2 class, you were given all kinds of integrals, and yes, some of them were quite difficult. But these are problems from a calculus book, so they're all contrived to at least be doable. So I'm going to give a couple examples. Where it's not an option. All right, so suppose you're given a curve that's defined by this kind of equation, just y equals f of x, where x is a parameter, between A and B. Then there is a formula that you would have learned in calculus. And that's this formula here. definite integral of square root 1 plus f prime of x squared dx. And it's actually kind of amusing when I'll be teaching about this in like a calculus 3 class, where what kinds of functions f of x would be featured in the exercises to make this expression, square root of 1 plus f prime of x squared, something that for which the antiderivative could be obtained. And there seem to be only certain categories of functions that for which was possible. So anything else, you'd be out of luck. And all you can do is try to approximate it using the ideas that I'm going to cover from this chapter and certain other ones too. So that's one example where even if a function f is fairly benign, and maybe f of x by itself is pretty easy to integrate, this expression might be just utterly impossible. And another example comes from statistics. So suppose you have a normal distribution with mean mu and variance sigma squared. Then, and you have a random variable that's following this normal distribution with this mean and variance, then the probability so random variable x. All right. Then how do you get this probability? Well, that involves evaluating an integral from x1 up to x2, and then you have to put the probability distribution function as the integrand, and that would be 2 pi sigma squared, and then we have e to the minus x minus mu squared over 2 sigma squared. Okay. So then you're stuck having to compute the integral of this Gaussian function. For this integrand. It's been proven that there is no antiderivative, at least in terms of elementary function. So all those integration techniques learned in Cal 2 will not help you with this. So again, it's necessary to find some way of approximating this. All right. Okay. So you actually, most likely, unless your calculus instructor was particularly negligent, you probably were shown at least a way of approximating integrals. In other words, these definite integrals, which you could think of as the area under a curve. You learned a way of doing that back then. What would be a way that you would have seen in calculus for approximating the area under a curve or definite integral?
Riemann.
Yes, a Riemann sum. All right. So this definite integral is approximately equal to sum of delta x times, so that gives you the width of rectangles from your Riemann sum, and then you'd have values of f at selected points, where these points that are chosen to plug into f lie between or lie within subintervals. So basically, you're taking AB. So let me get some definitions here. So we divide AB to n subintervals of equal width delta x. And the endpoints are given by this formula right here. As long as you could choose any point within each of these subintervals and get at least some kind of approximation to f, and as n increases, then your approximation would converge to the exact. From calculus, what were some choices that you had to make for choosing points within these subintervals? There are 3 in particular.
You could do endpoints, right endpoints, or was it mid or trapezoidal or something for midpoint, I guess. I can't remember if we did a trapezoidal type thing too.
Well, so left endpoint, right endpoint, midpoint is I choose x. In those cases, you're only approximating the integral, the area under the curve, with rectangles. Now, when you choose the midpoints, you're averaging the x values. Now, what you could do, instead of averaging the x values, you average the y values. So you plug in both the left and right, and then average those. That gives you a trapezoid. So that is so trapezoidal rule doesn't fall into the category of Riemann sum, but yes, it is a way of approximating integrals, and it's something that I will talk about next week, or I might bring it to this week if I'm bored. But yeah, so those are a few different ways. But except for using a midpoint, this is a terrible approach. And even the midpoint's not that great, but it's okay. And that's something we'll analyze in more detail a bit later on. And one of the homework problems I gave involves writing a MATLAB script that will compute a Riemann sum, and I think I said left endpoints. I don't remember, but it was either left or right. And the point of the problem is to see how large does n have to be to get the Riemann sum to be at least reasonably accurate. And what you find is sometimes that number of subintervals can be quite large. So we'd like to consider a different approach. Oh, by the way, I need to check on something something that might be of interest to y'all if you have the time. Sorry, quick digression based on the email I just received. Okay. All right. I saw this from LinkedIn, actually, but it's from one of my colleagues here, Dr. Julie Swickla, who is the director of the Center for Science and Math Education. So anyone who gets graduate degrees in math education as opposed to math goes over there. And she announced they have a Fall 2020 STEM speaker series. And the topic for tomorrow during the noon hour as a Zoom meeting is Dr. Erin Smith, who I'm not sure what, I actually didn't know about her, so I don't know what department she's in. She's here, though. She works with community organizations to build parents' math knowledge through hands-on activities. Her research examines effective ways to support parents to be math leaders for their children and community. And that's something that I thought was quite interesting, just because I don't know how closely you've all followed, like just over the last several years, the whole debate about Common Core, and it's something that is a very thorny issue that I could see both sides of. But I think a big part of a problem was that because of the very different ways in which today's children's parents learn math compared to how math is being taught today, that we're just, this is something we're not comfortable with and not knowing how to handle it. So I think it's something that parents do need some support about. So I thought, this sounds interesting. So what I'll do is, I had to email the admin over at CSME to get the link to the Zoom meeting. So I'll just take that email and forward it to y'all. So that in case that's something of interest to you and you would like to drop in, then you can. Okay. Now, we'll return to the matter at hand. Oops. Okay. So we want to have something that's more flexible than a Riemann sum. And we call that a quadrature rule. Let me check my notation here. Okay. Okay. All right, so our approximation will have this form. You can see it kind of looks like a Riemann sum, that we're evaluating f at select points, and then we're taking some linear combination of those f values to approximate the integral. And it's just an approximation, which is why we would have some error here. So these points that we plug into f, these are called nodes, and these numbers, the w's, are called weights. Now, if you like, you could think of the w's, the weights, as being like widths of rectangles, and then f, the value of f at the nodes, would be the heights of rectangles. So you could still think of it as being some kind of Riemann sum, but that doesn't necessarily help in terms of understanding where actual quadrature rules come from. But once we choose the nodes and the weights, those two things define this quadrature rule. All right. So Now, one criteria, though, for developing effective numerical integration schemes is so we want to get away with as few nodes as we can. Because if efficiency didn't matter, then we could just go ahead and do a Riemann sum and use a zillion subintervals. But we don't want to go down that path. Now, all right. So how do we choose the nodes and weights? All right, let's move this to a new page. Now, there's a couple questions that are helpful towards designing numerical algorithms in general. So they apply well beyond this problem. Okay. So are there certain functions that are easy to integrate with high accuracy or even exactly compared to others? And then if we have a function that does not fall into this category, what can we do to still take advantage of these easy cases? And we only want an approximation in the first place, so that's something to keep in mind as far as how we reduce general cases to easy cases. All right, so if you want to focus on what's a type of definite integral that's easy to handle, what would that be?
I was still mind asking again.
Okay. All right. Oh, you didn't hear the question? All right. So when it comes to evaluating a definite integral, what is a particularly easy definite integral to evaluate? Like, under what circumstances is this problem easy?
Like a constant function?
Okay, let's make it a little broader than that.
Like more cases that would be easy to integrate, or just
like, okay, a constant function, that'd be a type of function. Whatever type of function is easily handled.
Linear.
Okay, keep going. Constant.
Okay. Polynomial. Okay.
Yes, that was the magic word.
Oh, we did the whole last chapter. Okay, or chapter 7.
Okay.
All right.
Well, actually, hold that thought about last chapter because you're going to need that. Okay. All right. That was quite a tour of function land. That reminds me. Okay, sorry. This day's going to have digressions just because I don't have much to cover. But downstairs in this building on the second floor, there are a lot of math books just strewn around. Maybe not so much now, but people could just take. So one book that was languishing on some shelf was called Functions Modeling Change. And one of my colleagues thought that was kind of a ludicrous title because, like, well, what else are we going to be? Like, you have a function modeling a constant? So, but yeah, I guess it's all in the eye of a beholder, I guess. Okay. All right, so polynomials. So if you have polynomial integrand, then you're good to go. And you can get that exactly, except for a round off error. So that's particularly nice. So now the big question is, if suppose f is not a polynomial, all right, so suppose you're given some function f, maybe it's an exponential or a trig function, or who knows, it can be anything, but not a polynomial. So how do you take advantage of the fact that polynomials are easily handled when you have a function that's not a polynomial? What can you do in that case? And remember, we just need an approximation. It doesn't have to be exact.
So use polynomial interpolation.
Bingo. Yes, gold star for you. So we can interpolating f of x at the nodes, whatever nodes we choose. So these endpoints we use as our interpolation points, and most likely it makes sense to choose them to be within AB. And so now we have a polynomial of degree n-1, and that's one of these easy cases. So we evaluate that integral exactly. The way of putting it is the approximation of the integral is the integral of the approximation. So we want to approximate the integral of f. So we approximate f by a polynomial, integrate the polynomial exactly. Okay. So this leads to a particular type of quadrature, which is really the only kind of I'll concern us with in this chapter. That is interpolatory quadrature, which is exactly what I was talking about. Not just repeating myself, but oh well. All right. So that's what interpolatory means. That we're approximating the integral of f by exactly integrating f's interpolant. So then the integral is approximated by the integral of this interpolating polynomial. But now let's take a closer look at this polynomial, because we can write it in different ways. And the way that is helpful here is Lagrange form. All right, so then we have f of, actually use I, f of xi times Lagrange polynomial. So that's all I've done here is I've taken Pn minus 1 and written it in Lagrange form. And you recall from the last chapter, that's a linear combination of Lagrange polynomials, where the coefficients in linear combination are just the y values, or in this case, the f values. But then, whoops, it should be approximately equal to. Okay. I can use the linearity of the integral and pull some things out. I can pull out the sum. Just repeat this and then edit it. Okay, so summation and f of xi, all of that does not depend on x. So, because these are constants, because they're evaluated at xi. All right. And now if I put this in parentheses, whoops. Okay. Now, here we have this Lagrange polynomial that's being integrated, but this is a definite integral, from a to b. So this whole thing in parentheses is still just a number. So what I have here is a quadrature rule where I have the xi are my nodes, wi are my weights, and I now have a formula for the weights. So this is what sets interpolatory quadrature apart from other types of quadrature, because once you choose the nodes, that determines the weights completely. Because interpolatory quadrature always uses this formula to get the weights. And the weights are just the integrals of the Lagrange polynomials for your nodes on the interval AB. Questions about this? Now, one important term it applies, especially for interpolatory quadrature, but for other kinds too. The degree of accuracy, which is sometimes referred to as just the degree, is known as the highest degree of polynomial that can be integrated exactly using this rule. Now, what can we say about the degree for interpolatory quadrature rules? If your function f is a polynomial of degree n-1 or less, then f is the same as its interpolating polynomial so the quadrature rule in this case is exact. but what does that mean? We can say that the degree of any interpolatory quadrature rule is at least n minus 1. So if that is, so because of this, it's because in that case, interpolatory quadrature rule integrates the interpolant exactly, and in such cases, the integrand is the interpolant. We always have this, at least. But that is a lower bound. It is possible in some cases for the degree to be greater, strictly greater. In fact, what we will find is that it is the highest degree that we can get, almost double this, 2n minus 1. So that'll actually be the very last topic of a semester, is how to get that maximal degree of accuracy. Okay, I'll be covering some specific interpolatory quadrature rules later, but I just want to give one example. Oops. Simpson's rule. Okay, so what we have here is a surprisingly accurate approximation of the integral using 3 points, a, b, and the midpoint. So x1 is a, x2 is a plus b over 2, x3 is equal to b. So those are the 3 nodes. And then the weights, the first weight and the last weight are the same, b minus a over 6. And then the second weight is 2 times b minus a over 3. So, what's this b minus a over 6? Okay. All right. Notice if you take the sum of all the weights, they sum to b minus a, which is going to be true in general, because what if f of x is a constant? Then the value of the integral is just the constant times b minus a. So that's why I need all the weights to sum to b minus a. It's like with numerical differentiation. Maybe it's coefficients of your multiplying your f values, and they have to sum to 0 so that it could handle a constant function correctly. Same idea here, so that it can handle a constant function correctly. All right. So here we have these 3 points. It's derived by approximating f of x with a quadratic. interpolates at these 3 points, A and B and their midpoint. So Simpson's rule is an example of an interpolatory quadrature rule, where with 3 nodes, therefore approximating with a polynomial of degree 2. However, Simpson's rule is exact up to degree 3. So if I took f of x equal to x cubed, for instance, and I evaluated this expression, it would turn out to give you the exact value of the integral. So because it's an interpolatory of degree of using a quadratic, now tells us that the degree has to be at least 1, but it's actually significantly higher than that. So that's something that that can happen. In fact, this degree is the maximum possible for a. Oh wait. No, sorry. It's actually possible to have a rule that has 3 nodes and have degree 5, but still degree 3 is pretty good for something fairly simple like this. Now, one more thing I definitely want to comment on. I did not assign any homework on this bit, but it's worth mentioning anyway. Sensitivity. Numerical differentiation is an ill-conditioned problem. But since numerical differentiation, forget numerical, differentiation and integration are inverses of each other, it therefore makes sense that that it would go the other way. It is well conditioned. So, in fact, any error in the integrand f of x can be amplified by at most b minus a. And this is something that's discussed in the text where we estimate a condition number. Now, I did want to put this in the homework because I haven't really talked much about the condition number in this class. In 610, it'll definitely become much more of a thing. So the idea is if like you're going to incur some error in f, like by evaluating f at select points and so forth. But whatever error that is in f is not going to be magnified by some inordinate amount in the value of the integral. And that's what it means to be well conditioned. Whereas with differentiation, because you're subtracting 2 f values and you're dividing by h, where h is small, if there's some error in evaluating f, that could be amplified to a tremendous degree. So that's what makes the differentiation a bit riskier. Okay. But one thing to keep in mind is suppose we forget about the problem of evaluating the integral. Because remember, conditioning is a property of a problem you're solving, not the method used to solve it. So here to talk about actual integration. But if we focus on a different problem, the condition number of evaluating a quadrature rule, then what we have in this case, I don't know if I can fit it here. Oh yeah, I can. All right. It's actually the sum of the absolute value of your weights. And I actually took this from it's a solution. It's the answer to problem. Wait, not 926. This is a problem I did not assign. I didn't want to have take the time to go into all background about condition numbers and so forth, which is really actually covered in detail in chapter 2, which is not a chapter I covered in this class. Okay, so what does this mean? The whatever error there is in evaluating f could possibly be amplified by this amount in the error. Excuse me, in the error in the approximate integral. Now, well, what do we know about the sum of the weights?
Sum to b minus a.
The weights sum to b minus a. So you might think, oh, well, isn't this just b minus a? Well, actually, no, not always. It is in this case because the weights are positive. So yes, the weights will sum to b minus a. The sum of the absolute might not, though. And what is this? So the consequence of this, the reason why I wanted to spend some time on it, even though I haven't really gotten into conditioning this semester. Oh God, you're really going to make it spill to another page? Ugh, dang it. All right. Sorry, that just bugs me. So I'm going to cheat here and make this all appear in the same page. Okay. I'll show them. The way LaTeX spaces things is really aggravating sometimes. And that's why I give a whole lot of exclamation points. This is hugely important. If you're going to concoct a quadrature rule of any kind, make sure that the dang weights are positive. And for certain approaches that we'll see, in certain examples, the weights will indeed be positive, but there are some cases where they're not. So, for example, if you choose to design an interpolatory quadrature rule like this one, where the nodes are equally spaced points within AB, then it could actually be proven that once the number of nodes, like n, gets past 11, then you will not get positive weights. Or at least there will always be at least one negative weight in the bunch. And that's a huge problem because you might think, oh, as the number of nodes increases, then my approximation should converge to the exact integral. And it turns out that that's not necessarily true. If you'd say, okay, I'm going to compute an approximate integral using n equally spaced points, and let n keep increasing, and then my approximate integral should converge to the exact one. Well, then prepare to be disappointed. But there are other approaches in which positive weights can be guaranteed. And in that case, you really do get convergence. as the number of nodes goes to infinity. So something you have to be careful about. Now, notice the case that I said was a problem was equally spaced points. When else have we seen equally spaced points be a problem? And I know it's been a while. No, nobody. Polynomial interpolation, that function 1 over 1 plus x squared, also known as Runge's example. Yeah, so in that case, using equally spaced points, polynomial interpolant was awful, and that motivated the use of Chebyshev points instead, which greatly reduced the error. So, and the two things go hand in hand. That if you approximate f using a polynomial that interpolates f at many equally spaced points, then your interpolant is going to be inaccurate, and your quadrature weights are going to have some negative ones in there. So your approximate integral is also going to be a poor approximation. So you have to be careful when you're using a large number, n in this case, of equally spaced points. There's a type of quadrature rule that uses Chebyshev points instead, but we're not really going to get into that one. But there are other options that work well, no matter how many nodes you use, because positive weights can be guaranteed. Right. So this is one thing that I want to stick from this chapter. Got to have positive weights. All right, so interpolatory quadrature. Dang it. Fine, it's built over to number pages anyway. No. Wait. Fine. I'll fix it later. Okay. Interpolatory quadrature with n equally spaced nodes it's not possible to have all positive weights. So that's something that has been proven. I'm taking a look at that proof. I'm surprised that they could really exclude all the possibilities. It's interesting. Okay, so that's our tiptoeing into the water for numerical integration, but I'll dunk y'all's heads in soon enough. But it's also what we're finishing the semester with. Now, would I be correct in saying it because of the stuff going on in other classes that on Wednesday you'll probably still be between homework assignments? Or yeah, when's that real analysis redo?
So real analysis redo is Wednesday morning. It's on our own time. That's the time we all agreed on.
Oh, okay.
Mm-hmm. So I guess like after your research period is when it is. And then yeah. And then the ODE midterm is due tomorrow.
Oh, yay. Everything at once. Wait, so what time is the real analysis one?
It's at 10:45 to noon.
Ah, gotcha. Okay. Mm-hmm. Alrighty. Okay. Yeah, I got to figure out what I'm going to do with class on Wednesday because I've actually covered everything I planned to for the week. Although it's possible that I might not have budgeted enough time for future stuff, so we'll see. I'll have something for you, but at least by class time on Wednesday, all this other junk will be behind you. Okay, so all right, but that's all I have for today anyway. So good luck with all the things, and may you get through this week relatively unscathed. I'll stop the recording at this point.